Previously on Virtual Math with Mr. Ferrara.
Tangents.
It's Virtual Math with Mr. Ferrara.
Oh hey, I didn't see you there. I was just about to get started with our geometry lesson, 10-3 chords. If you'd like to join in, print out the PowerPoint and work the problems with me. If not, you could use your own paper. I look forward to our lesson today. Let's get started.
Hey, what's up everybody? Today we're going to be looking at section 10.3, chords. The first theorem is that if two chords in a circle are congruent, then their central angles are congruent. Again, if two chords are congruent, then those central angles are congruent. We can easily prove this with our triangle congruency theorems. So if you look at the picture on the right, NT, MT, PT, and QT are all congruent because they're all radiuses in that circle. Now, using the theorem that if two chords are congruent, we could then say that NM and PQ are congruent. What theorem would then say that this triangle and this triangle are congruent? Hopefully you said those two triangles are congruent because of side, side, side. So then because of that reason, this central angle and this central angle are congruent because of CP, CT, C. Corresponding parts of congruent triangles are congruent. Now the converse of this initial theorem is that if two central angles are congruent, then their chords are congruent. Well, if you look back at the circle on the right, if two central angles are congruent, then those chords have to be congruent. What theorem would tell me that the orange triangle is congruent to the blue triangle if these central angles were congruent? Hopefully you said side angle side. And if those two triangles were congruent because of side angle side, then NM would be congruent to PQ. The next theorem ditches the radius and just looks at the chords. If two arcs in a circle are congruent, then the chords are congruent. So if the arc NM was congruent to the arc PQ, then NM would be congruent to PQ as a segment. The converse of that is if two chords in a circle are congruent, then the arcs are congruent. Again, proven using the same reasons in the last theorem, just without the radiuses drawn in. Finally, we have a couple more chord facts. If chords are equidistant from the center, then they are congruent to each other. So if you look at this picture on the right, if TP and RP are congruent, then you know that AB is congruent to CD. Congruent chords are equidistant from the center. So if I have congruent chords, if AB was congruent to CD, I then know that they are equal distances from the center. When I have a right angle, the right angle means that these chords are being split in half.
So let's take a look at a couple examples using our chord theorems. So if you take a look at example 1, we want to find some missing pieces, and the only thing that's given is that angle B is 32 degrees. So let's start out by finding segment AB. AB is a chord, and the way we find AB is by knowing the fact that this section and this section are congruent. They're both 9 centimeters. Since the chords are equidistant from the center of the circle, that means the chords are equal to each other. Now, since there's also a right angle here and here, that also means that the chords got bisected. So if this piece is 12.5, all 4 pieces are 12.5. Easy math, this is 12.5, This section is also 12.5, so that means AB is 25. Second question is to find angle P, this large angle in the center of the circle. Now there's a couple ways we can go about that. One, what type of shape is that quadrilateral? Hopefully you said it's a kite, and we know that in a kite there's 360 degrees. So we know that we have a 90-degree angle up top, a 90-degree angle at the bottom, and we have 90, 90, and angle B is 32 degrees. And we don't know what the last one is, but we know that it's 360 degrees in total. When we do our math and we add these up and subtract from 360, we're left with angle P to be 148 degrees. I'll give you a little shortcut on these. Opposite angles are supplementary, so you needed to find out who was supplementary to 32 degrees. In other words, 148 degrees. Now BP is the last problem that we need to solve. We need to find this segment right here. Knowing that it's a right triangle because of this right angle means we should jump immediately into Pythagorean theorem. This section is 9 because the section north of it is also 9. This section is 12.5, and we're looking for a hypotenuse. So in this case, we have 9 squared plus 12.5 squared, and that equals this section, C squared, because it's across from the right angle. 9 squared is 81. 12.5 squared is 156.25 equals C squared. Add those two numbers up, you get 237.25. And we don't want C squared, we just want C. So we have to take the square root of that number. And the square root of that number, rounded to the nearest tenth, is roughly 15.4. So BP is 15.4 centimeters long.
Finally, there's 3 more special applications. These 3 applications basically say the same thing with different words. A diameter that is perpendicular to a chord bisects the chord and its arc. So if you look at the picture at the right, we have a diameter through the center of the circle. It makes a right angle with the chord, so therefore the chord is being split in half, as well as that arc made by the chord. Second application, a diameter that bisects a chord is perpendicular to the chord. Finally, the perpendicular bisector of a chord contains the center of the circle. If we have a perpendicular bisector, it goes through the center of the circle.
All right, let's take a look at our second example. In this, we want to find a couple, again, missing pieces. Now, we have a diameter, and that diameter is cutting a chord by a right angle. When we have a diameter and a chord, and when they are perpendicular to each other, that chord gets cut into 2 equal pieces. So if this AC was 7, that also means that CB is also 7. Again, when we have a diameter and a chord, and they're perpendicular to each other, the chord gets cut into 2 pieces. AB is the entire chord, so that's 7 and 7, which makes 14. Now DE is the final piece. That's a radius to this circle. Now DE, where it stands, is not helpful, but we can swing a radius anywhere we need to because radii are all equal. So I'm going to move this radius, and I'm going to swing it around so that it goes this way. And now it makes a right angle, and it makes a hypotenuse. So 3 is one leg, 7 is the other leg, and C is the radius of that circle. 3 squared is 9, 4 squared is 49, and that equals C squared. Add those two numbers up, you get 58 equals C squared. And the square root of 58, for the final step of the Pythagorean theorem, is 7.6. So this radius is 7.6, which means all the radiuses in that circle are 7.6, including DE. I hope this helps. If you have any questions, please email me, Schoology message me, or contact me on the Google helpline. We'll be going over this information during our live conferences, so come with questions and I'll be ready to answer them. Bye.